Welcome everybody to this OGG Gold Series for 2026, our third such series. My name's Neil Phillips. I'll be chairing this evening, and as part of a technical panel of Dave Craw, Julian Vearncombe, Jonathan Law, myself, we've put together this working with Henny and John and the OGG team that put all these together throughout the year. We've got a really interesting bunch of people on here today. When I go around, we've got someone from Alaska, we've got someone from Scotland, we've got someone from Russia, a few from Australasia, of course, quite a lot from Southern Africa. And if I've left you out, my apologies. But it really has spread much further and wider than we expect. The main reason or motivation behind this is so that we learn things. And we learn from these from putting together presentations ourselves, listening to others, debate, and so forth, sharing of knowledge. And I guess the key message that particularly John and I would sort of really feel strongly about is that this is inclusive in that they're free. People are welcome. You don't have to be the world expert. It's second years, third years, first year geology, undergraduates, postgrads, all very welcome to sit and listen or to watch the YouTubes later. So that's what they're for. And when I talk about the YouTubes, there's a playlist of 150 of these over the last 5 or 6 years. They're not all gold. There's some brilliant ones on diamonds. Some of the gold ones, if you're in greenstone gold, go back to 2022, this series. Listen to Caitlin Jones, listen to Alex Kisters on Barberton Greenstone Belt, Julian Vearncombe on structural control on gold. And that's the type of stuff that you can use anywhere around the world in that deposit type. This is a collaboration between Stellenbosch Uni, Melbourne University's Geology of Gold course, and that course has, it's finishing tomorrow. It'll be the 32nd year it's been run, working with OGG and trying to attract really good speakers from all around the world. And I think we've achieved that this year. I'm going to do something a little bit unusual after the next 4 or 5 slides. I've only got 4 or 5 slides now. I'll go through those just to introduce the whole series, and then we'll pass to Dave Craw. But I'm then going to run through about 6 or 7 very quickly with far too many words on them. That is deliberate. The purpose is to save them there on the YouTube so people can go back and read that later. I'm not even hoping to go through that slowly. Keep in mind, all these people, all of us, and speakers and commenters need to be challenged, because we only get better if we're challenged. Nothing should be accepted as gospel. And to a large extent, that's what this OGG Gold Series is about. Getting people on a level playing field and saying, hey, I don't really believe what you're saying. I don't understand it. Background to where we start. We had a very interesting series last March and April. We left some unanswered questions. Some we didn't really tackle, some we didn't really know, some we perhaps disagreed with. But what's the sedimentary setting for Witwatersrand gold? What's the source for significant placer gold? What's the sorting process that makes those reefs so rich? And the algal mats, where I don't think we came up with any clear evidence that they're originally. Some people thought they were, some thought they were later, and we thought, well, we better learn a bit more about that. And that's there. The other question that was put out towards the end was, what is the diagnostic evidence for any gold in the Witwatersrand reefs being detrital? A really straightforward question, and yet a really difficult question. And that was very illuminating. And it was illuminating because none of us could really come up with a quick answer and say, oh, this is the reason. And Andy Clay did something interesting. He then, given that we hadn't answered, he then took it away, that exact sentence, put it into ChatGPT, artificial intelligence, and that spewed out an answer. We'll call that A. That answer A was then given to the technical panel, and we critiqued it like you would a postgraduate paper, if you like. And then that critique went to, well, actually, Bruce Hobbs picked it up one morning and he gave his summary of what was going on, which is C. That is a really interesting set of things to look at. It first teaches us that you don't believe what you get just because it's from AI or comes from a computer. And it was also illustrates how if you say something over and over and over again, it becomes fact, which clearly is not good in science. That's really where we're up to. And I'm going to go through 4 or 5 slides quickly just to get them on the screen. South Africa, way ahead of anywhere else in gold per square kilometre of land. List of speakers with their bios. Last year's series. The gold conferences since 1982 all around the world. And I flagged this one. See Linda's on this lecture, so is Julian. And that's this planned for next year, our gold series. And I guess the other thing about an informed base, if we're going to talk about placers and not placers and other things, let's go and find out about them. So we've had a gold placer field trip in Otago, New Zealand with Dave Craw, and we've got another one starting in about a week in the Victorian Gold Province where there's 50 million ounces of placers, and it was one of the world's great fields in the late 1800s. Martin Hughes and Stephen Carey are the experts on that, and they're leading a group, as I say, in about a week's time. That's it for me. I'll go through these very quickly as Dave Craw gets ready. Background last year, Julian Vearncombe pointed out that there may be a source, and I think we need to go back to his work and sort of challenge that, question it, and think about it. A bit more fleshing out of what the background is this year. And we now go on to modern placers and Dave Craw. So Henny, I think it's right for me to now stop sharing. Dave Craw to get up and running. And my opportunity to introduce him. And I'm not going to give a big introduction of the speakers tonight. The three of us are actually summarising a little bit from last year and what's gone on in the intervening 8 or 9 months. Dave has worked on placers and many, many other things in South Island, New Zealand. He's been at University of Dunedin for much of his career, and we're delighted he can join in here. So Dave, when you're ready, you take over.
I think I'm ready now. Can you hear me?
Yes.
Oh, well, that's all good. So the first slide is actually intended to be provocative. It grew out of last year's series of talks, and it just identifies something that we don't actually know a great deal about, and that is if you look at Cenozoic, in my world, mostly Pleistocene placers, they have certain characteristics, and they're in blue there on that slide. And as far as I can tell, I'm not a Wits expert, but as far as I can tell, none of those things apply to the Wits. So that leaves us with the situation that the Wits is claimed to be a placer, but it doesn't look like a placer. Any modern placer anyway. The thing about Cenozoic placers, they're narrow fluvial channels, and almost all of them are in basement. And they're made up of residual gold. And I'll just go on, if I can work the technology. I thought I was working the technology. There we go. So this is a New Zealand placer. It's a combination of Pleistocene and modern. And it's a deep channel. It's about 2 kilometres deep from the top of the mountains where the original gold comes from, in gold quartz veins. You can see up on the high mountains. This is actually a very deep channel all the way down. So this is the modern one down here, the blue line, and then there was a Pleistocene one up here with the dashed light blue line. And again, it's channels, and they're channels cut into basement. Now I'm going to try and do the technology of, we'll go on. And I've made a cartoon. And this is how Cenozoic plasters, or most of them, form. And it takes quite a long time. And it's like running on the spot. So you get a pile of dirt up in the top left that might have a grain of gold in it. And then, and that grain of gold will be dispersed through a big pile of sediment. But after a 100-year flood, and I'm just making up these numbers, the bigger boulders and the gold will be down on the basement, the bottom of the channel. And then we'll go through another cycle. And again, and again, and again. So in the bottom right, we're starting to get a placer. So we need this constant recycling, reworking, removing 99% of the sediment to lead the gold, some black sand, which is usually iron minerals, and big boulders. And this is what they look like. On the left, there's a few boulders there. This comes from a modern placer river, active river, and the dredgers just pulled these up. The dredgers dug, whoops, sorry about that, dug down to the basement, pulled up the big boulders and threw them away, and then worked the finer sediment. And on the right-hand side of the screen, this is the remnants of a channel that was left behind when the miners worked a late Pleistocene placer. And just to emphasise this point, it's actually really hard to find places to take pictures like this because the old timers worked them all. The one on the right there, they left that behind, presumably because it didn't have enough gold. But again, you can see this is sitting on basement schist in this case. I threw this one in just because I was in this mine the other day. But one of the really distinctive features of these channels is they have this black sand. The black sand is with the gold. You can't separate gold and black sand in a sedimentary environment. It's hard enough to do it in a mine. In this particular mine, the gold's too fine to even respond to mercury. It's actually really, really hard to separate gold from black sand. In this situation, in the top right up here, this is the channel with gravel, and there's water coming out of the mine pit, and so it's washing out the matrix. So this is the black sand, and the gold is in there, and very difficult to separate. This is a point that nobody has been able to explain to me with respect to the Wits. So I'm actually really interested to hear about this because this black sand aspect is quite a big deal. Now I want to compare what I've just been describing with a braided river system. We have a lot of those in New Zealand. This is an active one. It's got Pleistocene gravels on the side, but the point here is that there's no basement. This is a braided river outside the mountains, downstream of the mountains. So all you've got on the side is more gravels, more and more gravels. And the thing about these, that the channels are maybe 3 metres, but most of them are not that thick. They're very small, and they migrate laterally. But as a result of that, you don't get that reworking that I described before in a basement-hosted channel. That constant addition of material and then removing most of it, and then adding more and then removing it. That doesn't happen in these braided river systems. So there might be a few bits of black sand on a point bar somewhere, but that's temporary. It'll be gone in a month. And there's no reworking to enrich that black sand. All you've got is a few bits of ilmenite, maybe a zircon or two, and on a good day there'll be a grain of gold. And you'll never get more than that. This is what they look like when you get inside them. This is an outcrop of Pleistocene stuff, and you can see what the channels look like. They're really diffuse. They migrate laterally. They're only 2 or 3 metres thick and no enrichment. If you wanted to enrich black sand with gold in this system, you would have to erode all of this down to something like 10 centimetres thick. And even then, it wouldn't be a very rich deposit. So, just to be provocative, this is the picture that I have seen many times with respect to the Wits. Somewhere in the background, there were mountains. They're not preserved now. There may well have been places there on the basement. But once the rivers got outside the mountains, and that's the bit that is preserved in the Wits, there's no opportunity for concentration until you get to the coast. And at the coast, there are linear places, not great sheets, over along the shoreline, so they're parallel to the shoreline. And that's me. That's me trying to be provocative. I want to know more about what the sedimentologists say about the Wits sequence. There's been a huge amount of work done on the Wits as a sedimentological study. So I hope during this series of talks we'll hear more about that, and in particular about channels. What are they like? And is it likely that you could get concentration? Is the black sand? Where is the black sand? Is it all pyrite now? These are questions that I can't answer because I live in the Cenozoic. The oldest rocks within any distance of me here are Triassic. So I'm a Cenozoic man. If you people can tell me about the Archean, that would be great.
Okay, that's fabulous, Dave. There's the challenges out for people. We won't take questions and discussion now. We might at the end of Julian's talk, but we've also got several other weeks, and we also have discussions during the week. So if people want to fire out questions and say, what about this or that, please do so. I am just about to share my screen, Henny, and hope that works. How's that look?
It looks good.
Okay. So, number 2, when I can't make myself exist. That's all right. Metamorphic fluids and gold. And we talked about these a little bit last year. And part of the reason was if we're going to be discussing places, if we're going to be discussing fluids and other things, we all need to sort of bone up on them and learn a little bit so that we can have discussions with have some discussions with a bit of sort of intelligence and solid geology behind them. Metamorphic waters and their golden wonder. I'm going to talk about the bound water molecules in minerals, diagenesis versus metamorphism. They are quite different environments for the purpose of the fluids. Green schist versus amphibolite. Just one of many transitions, but a particularly important one for us and a good one to talk about. Hydrothermal fluids, gold into solution, sweeping isograds. And I will not talk about source regions, but there's a whole we could have a whole session on that, on what the source region for these metamorphic fluids look like. It has been studied. It's been studied in several parts around the world. So the puzzle is, can we really move through fluids through solid rock? Can we get gold into solution in nature? And Des Pretorius, for example, said an emphatic no and no to both of those. And I'm not particularly having a go at him or anything. I'm just saying that is a reflection of what an awful lot of people thought at the time. And I'm talking about the 1960s, 70s and so forth. And that's in writing over and over again. He was not correct. I think most people agree today that fluids move through rocks. But we've got to keep in mind that an awful lot of people were brought up on just what he said and to some extent took it for gospel. The world's moved on. The world's moved on particularly because of people like John Ferry and Bill Fife and others in the 70s talking about waters in the crust, this revolution that took place. And it took a little time to move across to other places. People like Russell Myers, Jonathan Law, Julian Vearncombe were key in promoting that in the 1980s and bringing in ideas from outside on fluids. When we talk about fluids in the crust, we've got meteoric or percolating rainwater, seawater, diagenetic fluids, magmatic and metamorphic. I'm quickly going to talk about the difference between the diagenetic and metamorphic ones. The diagenetic stage, up to perhaps 200, we won't argue about temperatures, but roughly you've got grains here. Between the grains, you've got space, and that can be filled with waters of some type. You've got other grains here that might be bits of carbonate, bits of shell, bits of rock fragment, bits of micas, clays, and so forth. And ultimately, when that gets squeezed a little bit, everything gets squeezed out. And that is diagenetic water that heads off. It could be saline or not, but that's not what we're interested in. When the rock gets to the metamorphic stage, and we'll now put a temperature of say 300 on it, 400, 300, there's no gap. There's no great big holes or porosity, no permeability, but fluid still moves through these rocks in a very different way, and that is through cracks, microfractures, fault networks, and so forth. So we might call that hard rock, and that's really what we're dealing with. That's actually a thin section with grains of quartz and feldspar, perhaps micas and so forth. Now, in those rocks, we're interested in clays, micas, and particularly chlorite, because it's well outside the diagenetic range. Minerals like chlorite, for example, still have OH in their structure. Now, that OH is not sort of come and go, just heat up and goes off. That is essential. If you don't have that OH, those OH layers, you do not have chlorite. It's as simple as that. And the same would apply for kaolinite and micas. It's an essential part. It's part of the structure. And something like chlorite, depending on the composition, can have about 10% water. And that doesn't sound much till you consider 1 cubic kilometre of rock, chlorite rock, could be a tenth of a cubic kilometre of metamorphic waters. Let's look at the green schist to amphibolite facies transition, something that's been studied for 100 years at least. The underlay of this with the different facies really dates almost back to Escala in the 1920s. I've put on that my own calculations. There's nothing sophisticated about those, working out it's about 5% water perhaps for chlorite rock here, 1% for an hornblende or amphibole rock here, and a pyroxene granulite, pyroxene quartz, plagioclase ilmenite could have nothing. Now, what that's saying is the metamorphic assemblages are telling us we've lost a lot of water going up there. And Bill Fife realised this, and he said, this is a big issue in the crust. But if you don't believe that, we can analyse that rock, and analyse that rock, and simply look, and we'll see the volatiles change dramatically. So it can be confirmed by analysing and testing. So we're going to look at that green schist amphibolite facies boundary or transition. The key minerals are chlorite, perhaps actinolite and other things, and the key mineral over here as well, it's hornblende plagioclase, the diagnostic assemblage for an amphibolite facies rock. Green schist facies here, the green is chlorite, This dirty stuff here is carbonate. There's a bit of quartz, a little bit of pyrite, and a little bit of iron oxides. And for the igneous petrologist, you'll see there's a pseudomorphic texture after ophitic, what was feldspar and clinopyroxene intergrowths in that there. And at amphibolite facies, that same rock becomes plagioclase rich here, hornblende rich here, a little bit of cummingite, a little bit of quartz, and a touch of oxide, iron oxide. So there's a change. It's a complete change from one to the other. And we can put numbers to that quite easily today. Green schist over on the left, up to about 7 or 8 kilobars there. We're not particularly interested in pressure. It's the temperature that matters. Amphibolite over here, temperatures 400 to 500, somewhere in that range. We're getting this big change from green schist facies to amphibolite. And where's amphibolite? Well, it's hornblende plage, hornblende plage, hornblende plage, hornblende plage. So a whole series of amphibolite facies over on the right, green schist on the left. And between the two, we've got these contours of the amount of water that's released. So we can actually calculate that 2, 3, 4% of water is lost over 20, 30 or 40 degrees. It has to go somewhere. So the metamorphic fluid is evolved around about 450 degrees from that last diagram. In actual fact, it ends up having, can have, depending on the assemblage, up to 20% CO2 in that fluid. Breakdown of a little bit of pyrite, and there's very often a little bit of pyrite in these green schist facies rocks. One gets H2S in the same fluid, and there's no chlorine in any of those minerals. So there's low salinity of the final product, the metamorphic water. So it's a low salinity fluid with water, CO2, pyrite, and gold. Come to gold in a moment. That sweeps through the whole rock so that all your green schist gets converted to amphibolite facies over vast areas, either surface area or volume. It includes gold at the moment it forms. It's a global process, meaning it can happen in China, it can happen in Scotland, it can happen in the Abitibi Belt, it can happen in Zimbabwe. And it can happen from the Archean to today. There's nothing special about time or anything like that. Now this is looking at, that's the assemblage we saw earlier, chlorite dominated in green. It goes to this amphibolite hornblende dominated assemblage here. And in the process, virtually everything is destroyed. And 5% volatiles go off and there's a complete conversion. Now, as those volatiles go off, they go off as a water CO2 H2S fluid. And these dots here, they're not chunks or grains of gold. They're my representation of atoms or nanometric gold, if you like. And in contact with or involved with that fluid, it'll immediately take the gold out this way and not across here to the right. So there's a loss of gold in the rock from here to here. And lo and behold, that's been demonstrated in places like Otago, South Island, New Zealand. But we're interested in the fluid. The fluid is water CO2 H2S with gold. The gold's bonded to the sulfur and the gold atoms go into the fluid. Well, it's a great way to concentrate all that gold from the ppb level in a normal rock. And the fluid is gold bearing from day one. It does not have to go off through a large rock mass to pick up gold somewhere else. And you can have this isograd, if you like, or the transition sweeping through a rock mass, and you go from chlorite with a little bit of gold to amphibolite with a little bit less gold. Or you can turn it around this way and it sweeps up through the crust, and you're basically pushing, if you like, pushing a gold-bearing fluid ahead of you. And this is really along the same line that Julian Vearncombe's email of about 3 weeks ago was saying that this is a group of Stellenbosch honours students. Table Mountain is on the left. We're looking down at Cape Town here. That's 20 square kilometres, so 1 kilometre thick slab like that. And you can see it's got 100 tonnes of gold at the 2 part per billion level, which is crustal background average. So nothing special there, no gold deposits, no chunks of gold or anything, I assume. And you've got 3 million ounces there. And now just think what that's like when you've got more over here and all the way around here and all the way there and all the way back through the country. So you've got a huge potential for gold if you can make this work. And that's the key. It's the mechanism to get gold into solution and move it somewhere. Sweeps through rock very effectively, that process. Gold as it forms, so it doesn't get collected somewhere else. It's a global process from the Archean to today. And you need heat energy. Well, that's the metamorphism part. Chlorite, which could be in mafics or grey wackies. Carbonate, necessary part. Pyrite, necessary part. And probably the easiest part of the lot is finding some gold at ppb level, because that's just background in everything, plus or minus a bit. So that's really how you'd make a fluid with gold through that type of transition. It is written up in that paper there, and I've covered it in my book. I'll finish there, stop sharing. I'm going to introduce Julian Vearncombe in a moment, and when he gets ready. You want me off, don't you, Henny?
Yeah, would Julian come on?
Vearncombe needs to be unmuted. There we are. Wonderful. Julian's a consultant in Perth. He's published extensively on structural control of gold deposits and other deposits, worked in the Yilgarn a lot, but many other, particularly Archean terrains around the world, and including being in South Africa for a while, at which stage he picked up really important ideas on the greenstone belt gold and on the Witwatersrand, which we're working on together. Julian, take over, and I'll get out of the way.
Okay, can you see the slide with the word rheology, and can you all hear
Yes,
me?
yes, we can.
Okay, well, I thought that Dave Craw and Neil Phillips wouldn't be controversial enough, that they wouldn't say anything that would upset anybody. So I decided that I will set about arguing why rheology is arguably more important than sedimentology, stratigraphy, and geochemistry. Now, I have covered myself with the caveat in the last sentence of the last slide, but up to that point, you are encouraged to collect all the examples that I can be criticised on as we go along. I really want to make the point about rheology, because in the email discussions we were having, I did detect that a lot of people didn't really quite grasp how important rock strength is. Now, I do have to deal with one pedantic issue, which of course is it's not the absolute value of rheology. It is the strength of one rock relative to the rock that is adjacent to it. And even that's not enough, because it's also the strength of the rock in dilation as well as the strength of the rock in compression. So let's go on to the next slide, if I know how to do that. That's interesting. Oh, there's the next slide anyway. Now, this is a photograph that was possibly taken on this planet. It was posted by somebody who lives in Ecuador, but is Colombian, or somebody who's Colombian who lives in Ecuador. And it was this particular view that got many of the structural geologists around the planet commenting on LinkedIn. But this shows how just dramatic rheology is as a control. Now, in this case, it's a control on dirty quartz veins. But how do you get a process whereby this rock here, this bedded shaly rock, is not veined, it's not showing the dilation, yet here we've got a unit that was probably not a conglomerate in this case, but a quartzite probably, and it has enjoyed massive dilation and extension. And the whole point is that these two rocks have very different physical properties when subjected to the same temperature, pressure, fluids. And you can see, if you look in detail, the veins, how they even track in the fibers, how they track the opening of the veins. So let's just go on to the next one. So this is a Waterstrand type gold system in northern Portugal. I only visited it once because we didn't succeed in buying it, but I've got this photograph from that. And here we've got these shaly units with no quartz veining, no fracturing. And here we've got, it's not a conglomerate, it is a quartzite, or I should say a dirty quartzite, with a whole series of fractures in there. And what we're seeing here is the massive difference between that rock and that rock. So here on a simple graph, this is far simpler than anything you ever hear of from a geochemist. This on this axis is the downward push, and this is the sideways shear. And to the right of the origin, it is in compression, and to the left of the origin, it is in tension. And these are the two failure curves, not drawn from theory, but drawn from what we know looking at these rocks, that the shale at these metamorphic conditions, and I emphasize that we are below the experimental and the petroleum windows here, the shale is not deforming the way that the quartzite or conglomerate deforms. Now, there is an argument that because this is probably deforming plastically, this is deforming elastically to failure, and this is probably undergoing metamorphic changes, that perhaps you shouldn't have the two on the same diagram. But for the sake of getting this message across, I do that. So one is much stronger in extension than the other. It is the conglomerate which seems strong in compression, which is weak in extension. Hence, we can deform that, we can mineralize that, and since it's a Portuguese gold mine, the Roman slaves could mine it for the Romans. And the rock here has got much less to almost no gold in it. So let's have a look at some typical Witwatersrand material. And in the paper that was published last year and the subsidiary material, which was a PowerPoint made into a PDF, available on the web for nothing, we took a whole series of photographs that were taken to show the sedimentology and the stratigraphy of the Witwatersrand. And they had almost no mention of the structural geology. And just like this, none of these descriptions here of these rocks here mention the most obvious thing in the photograph. And the most obvious thing in the photograph are these fractures. And all of them show a whole variety of fractures, a whole family of fractures here. But even these show fractures like this, fractures running across, fractures that pass from one grain through matrix into the next grain. In this particular one, we've got a dramatic fracture up there. We've got a series of fractures here running through there like that. A fracture here running up like that. These are not fractures peculiar to one grain. They are fractures that are imposed on the rock sometime after diagenesis. And I don't understand how for so long, something so obvious, something in every sample has been ignored. And now I lead to the point where I will probably be cancelled forever. No, sorry, no, with the slide after this. So the Leeds group, and Anglo-American and Keith Kenyon looked at these in great detail, and all the gold they found was on microfractures. And I'm not going to go into any further detail on that, except to say that it's extensively documented, and we'd like to see more of that documentation. Now I will get myself cancelled forever, because this is a rock, at the front of the department at the University of the Witwatersrand. Now, I don't know whether I've got this the right way up or not. And I do know that way back in the personal Archean, I had a conversation with Steve McCourt about this. But this rock is full of fractures. A quartz vein down here, a quartz vein down here. One I didn't label down here, a fracture going along here, a major fracture going through here. It's probably more than just one. Lines of fractures through here, fractures going up through here at different angles, and a whole series of fractures here that go across the rock. There are also some fractures, but also a zone through here, which is dominated by fine-grained minerals and sulfides and clasts of quartz sitting in another matrix. What I say is, desperately, we need somebody to study the deformation fabrics in this rock and stop worrying about the sedimentology. And I suggest that this afternoon all lectures are cancelled at the University of Witwatersrand and the students can supervise the professors mapping the fractures out. Does this mean anything? Well, in economic terms, and I keep coming back to this, which Greg Hall showed me and lent me and allows me to use, which is two of the drill holes that were drilled by Placer. And we see how we have these high-grade portions, but they have low-grade envelopes. So not what we would be expecting in a placer, but the sort of thing that we would be expecting if the fluid has passed through those other rocks to the super duper greater than 8 gram per ton high grade. So this is a graph, this is linear, and this is a log graph showing, and then the same for another drill hole. Again, I don't understand why this has been floating around the industry for 4 or 5 years. I don't understand why we're not being shown many more of these, either in support or to say, hey, there's a problem here. Now, I'm not going to talk for Joan Cowan or Bruce Hobbs, but they've been modeling exactly this sort of thing. So where they're calling reaction site, here's your rheologically strong unit. Here are your metamorphic fluids fluxing up, no special source, just fluxing up from beneath, focusing into these narrow positions and then escaping up here. And these are what Joan will call Perkins discontinuity. And lo and behold, here are our reaction sites. I'm not going to justify their science in detail. What I am saying is that there is a science available. I did comment to June that the model was all very simple and it wasn't really that good for the Witwatersrand because they've only modeled it as one horizon and they should model it as multiple horizons. And I can't tell you June's reply to that. Now, when we published, we did miss a number of papers, and some of those papers were by Musa Manzi. And some of his papers are showing more seismic in the southeast of the Witwatersrand, which is probably not quite as deformed as we implied. But I also had a look at this Kloof paper of his, and this is just a single image in a publication. And I had an interpretation, and I got the two tame geophysicists that I know that I can get free consulting from to go over this. And both of them are of the opinion that this must be showing a duplication, a thrust duplication of reefs, a thrust duplication of strata, possibly reefs, but we don't know that, at the Kloof mine in the seismic data. Now, this comes with 1,000 caveats. We do need 3D seismic interpretation. We need whole of basin models. But these rocks are a whole lot more deformed than has been acknowledged. And this compressional deformation may have been happening at the same time as that sort of extension in the rheologically strong units, the conglomerate, or it could have been at another time. So the sort of model that you've got, and Dave didn't really apologize, but obviously to a South African audience, you don't want to hear this particular word at the moment. But the model from New Zealand is not of big things coming up faults. It's not of granite supplying anything because there are no granites. It is a metamorphism here, that chlorite out reaction that Neil showed you, passing through the zone from down here, where it's essentially creep and fluid motion is along grain boundaries and deformation is plastic, to this upper seismogenic zone where you've got elastic deformation to failure, and fluids will pond, and then they will move through transient porosity waves through here, and we can get widespread gold mineralization. So taking that model that works very, very well in New Zealand and Taiwan, can we put it into a South African context? I think we can. We would have that transition through a broad and far too neat in this diagram, brittle ductile transition. We can source at depth, either in the rocks beneath or within the basin. And there is an oversupply of material here. There's no shortage of material. And then mineralize at these particular boundaries, such as the Ventersdorp boundary with the Witwatersrand and the reefs that are sitting in these sorts of positions. So conclusions. The first is that this sentence here was written last year by 2 Chinese and 2 Australian authors. The Witwatersrand reefs lack the complex brittle ductile transpersonal structure architectures and auriferous quartz veins that typify orogenic gold deposits. I am saying that 100% that is observationally incorrect. Witwatersrand gold is on microfractures in rheology units that are strong in compression and weak in tension. Metamorphism is good enough to supply not just all the gold, but we have to go to the point of asking, where has all the gold gone? Where is the rest of it that would have been supplied? We need to work on raw grade data, not Krigged, not contoured. And if you disagree with me, go out there and show us a Witwatersrand reef without the microfractures and without micro gold on fractures. And finally, rheology is the science. It's the new science and it's the important science. But I do have to concede the caveat that, of course, the rheology is a response to the chemistry and the sedimentology. And they will, as science develops, become subsubjects of rheology. Gold 27. It looks like we've had a few hiccups, but Linda's done a sterling job of solving those. We've got dates. It looks like it's going to be at Gold Reef City. So just in the middle of a session, you can pop underground and have a look at what the Witwatersrand looks like. We want you to come and support us. If you've got any spare rand in your pocket, we want you to be a sponsor. We want you to come and promote your business. We want you to submit a paper, a poster. There will be short courses. There will be field trips. There will be mine visits. Some possibly not just limited to South Africa. And we're going to kickstart the Witwatersrand Legacy Project. And we are going to change perceptions on South African gold. Now I have to ask if there's anybody still there, if everybody's left me.
I'm still here. Thank you, Julian.
Only just.
What I did flag to people is I can't get. Oh yeah, no, I can't get myself back on. I'll take a question or two if people have got it, but we'll also come back to some of these topics again. They're sort of basis really to go a bit further forward next week, the week after, and henceforth. So has anyone got a question or two they want to ask? I don't see any in the chat. While you're John Parnell, go ahead.
Can I just invite Dave Craw for the benefit of all those people who are learning to explain what a black sand is, because that was the really the basis of his talk, but there was no explanation of what it is, what it's composed of, and why we get them.
Yeah, that's a good question. I was vague because the actual content of black sand it varies from place to place. Some of our black sands are actually red with garnets, and some of them are white with zircons. But most commonly they're black, and they're made of magnetite and ilmenite.
Right.
And
okay. I'm just asking for the benefit of those people who are at the learning stage here.
So, Dave, why isn't the simple answer that all the pyrite used to be black sand? Therefore, it is there in the Wits.
Yeah, well, that may well be right, but I think the grain size is not right for that. I mean, I have views that we can argue over a beer in that, but one of the things about the black sand in a Cenozoic placer is that it's sand, whereas all the clasts are bigger, a lot bigger. And
Right.
pictures I've seen of some of the Wits conglomerates, the pyrites are much the same size as the pieces of quartz. Is that not right?
There are all sorts of different types of pyrites that have been defined and classified. Yeah, but people think of them as pyrite rather than has been black sands.
Yeah, sure.
I think you're still talking as if you understand, as if you know a lot of geology. My impression is that there are people here who are learning and need to know why an accumulation of black sand occurs.
Oh, all right, fair enough, John. I can see your point there. The black sands that we have are relatively dense minerals. So a piece of quartz is density of about 2.6, 2.7, and a piece of magnetite will have a density of about 5 grams per centimetre cubed. So these dense minerals tend to be finer grained than the silicates. And when you get the repeated concentration and reconcentration and reworking, you get an accumulation of relatively dense minerals, and gold is one of them. But normally the gold is in a minority, a big minority, and the accompanying heavy minerals are things like zircons, garnets, magnetite, ilmenite.
So the key point really is that you need a substantial erosion of a basement source, which goes through several cycles of erosion and redeposition in order to get to that point.
I wish that you'd given my talk, John. That's much clearer than what I said.
We got any other questions?
Linda says there is something black in the Wits. It's called carbon.
I
That's
Neil,
John's world.
So who's on?
Nick?
Okay, go ahead.
Nick, you wanted to say something, Nick?
Yeah, I just wanted to make a specific remark. I thought you solved the black sands problem for the Wits.
Say that again. We didn't hear that, Nick.
Hello? You have trouble hearing me.
Yes,
So I
just
thought,
speak slowly.
Neil, you solved the black sands issue for the Wits. Done
Okay.
and dusted.
I'm not hearing that clearly. I think the
He
connection.
says you have solved the black sand
I'll,
issue for the Wits. Done and dusted.
I'll write the comment down afterwards. Yeah.
Well done, Dave.
Neil,
Yes.
can I just
Go ahead.
ask? Julian put a diagram on the in his talk on the Wits Basin. Are there basins or a basin? You know, that number of 14 kilometers Julian showed, is that sort of generally accepted? Obviously, you know, we know there's been lots of repetition, you know, faulting and that sort of stuff. But, you know, we should have a pretty good handle on how big that original basin was. And I'm just keen to know in terms of temperature, pressure, heat, mineral flow, you know, fluid flow, how porous and how active it was in a basin like that.
I think that the numbers that I used were all taken from the standard stratigraphic literature. In most cases, I then did things like halve them in case of erosion, loss, things I didn't know about. The calculations only went to a dip, a gentle dip for the Witwatersrand of 35 kilometers. So only a part of the Witwatersrand basin is needed to supply the gold. I mean, I think you're making the same point as I make endlessly every time I talk, that it is ridiculous that we have all this seismic. Some of it has possibly been given to the universities, and we still don't have a complete basin model, which is just something we desperately need. I'm not persuaded that porosity, I mean, it's not about a permanent porosity or something that you can go and measure. We're talking about something that happens as a transient wave. Some people have called them Connolly waves, and they enable you to move fluid laterally through the upper middle crust, just above the transition between the mostly ductile and the mostly brittle.
So that what we must be doing, Julian, and I guess Neil will be doing that, is again, you know, a list of questions is why haven't we done, you know, certain of these things, and why don't we have a decent basin model or basins? I'm just interested, and I'm by no means a bit expert on you know, back then there was no vegetation. You know, how does that impact flow and stream formation and the whole, you know, different fines material in that basin? And I come back to, you know, there's an immense amount wonderful work done on aquifers, for example, the Table Mountain sandstone. Again, you know, it's not as big as the Wits, although it's probably more laterally extensive. And the brittle fracture, you know, at the base of these amazing TMS deposits, Table Mountain sandstones, the brittle fracture is huge, and the aquifers are remarkable. So, you know, again, you know, fluid movement is very prevalent. But I really think out of this, you know, series, we must have some hard questions and a list of the things that are outstanding, and go and really pinpoint and try and find where the data is, or where where we can answer some of the critical questions.
Well, I mean, I think that just some thin sections of the rock at the front of the geology department at Wits University,
Yeah.
and look at the deformation textures, and answer the simple question. In that sample, where in detail is the gold?
Okay.
And,
Good.
there's been a good question asked. What's the particle size? And an answer is sub 10 microns. There might be a bit that's bigger than that from what I've read, but yeah, I think sub 10 microns. That's pretty small gold for a placer.
Yeah. But then it also says, except when sheet-like gold between hydrocarbon spindles.
Yes.
So
So
you get higher
Yes.
variety.
Just for comparison, for everybody, the classic published type of numbers for a modern placer would be 500 to 5,000 microns. That's in the literature. I'm not quite sure what it is in New Zealand, Dave.
unfortunately, it's a bit smaller than that, but
Yeah.
right now I am actually working on micron-sized gold that the miners have been losing. So yeah, we do have gold that small, but 90% of it or more would be more than 100 microns.
Yeah. And I see Nick Fox has answered in the chat box.
Yeah.
Thanks, Nick.
Okay.
We got a final question from anybody?
If nobody else
Actually, I have
wants
a
to make a
question.
comment, no, carry on.
Sorry, I have a question. Because the image, sorry, Dave, the image that you, here is Linda. Dave, thank you. The image that you show of the placer is actually a breccia. It was boulders of different sizes, and it's not really a conglomerate.
Yes, some of them are breccias. There's usually a mixture. I showed a picture of boulders who are well rounded, and some of those have come 100 kilometres. We have big floods here.
And
They're
the
huge
heavy
boulders.
mineral in a thin section, are they rounded? The heavy mineral, not the gold. What do they look like?
For a fluvial placer, the heavy minerals will be rounded. Yeah. They can travel 100 kilometres too.
So can be this buckshot pyrite or this pyrite in the Wits actually a sulfidation of heavy minerals, magnetite or ilmenite?
Well, that's what Neil is very keen on, I think. It's just that I've seen some very coarse pyrite there, which doesn't fit with my concept of the usual black sand. But it may well be right.
I'm just thinking because some of this buckshot pyrite have this concentric layering, like you have it in the hematite, in the iron ore.
I think that's more likely.
And you could sulfidize that and you replace the hematite or magnetite with sulfur, and then you have your buckshot pyrite.
I think the BIF, the banded iron formation sort of thing is much more likely than, say, an ilmenite. We just get a lot of ilmenite.
This is what you wrote in the Archean. You have the banded iron formation.
Yeah. That I think is much more likely. I think that's a good story. Can anybody prove that?
Yeah, well, we'll take out thin section and share them with Niels and see.
Yeah. Well, Neil has looked at.
Sorry, Julian.
Neil has looked at replacement. He's got thin sections for replacement. Isn't that right, Neil?
Lots of, replaced banded iron formations, replaced chert pebbles, replaced garnets. Yeah, there's lots of it.
Yeah. I think that's a lot more likely than the stuff that I call black sand. Ilmenites and magnetites. Zircons.
It's interesting because chromite, it didn't got sulfidized because there is chromite and diamond in this black sand of the Wits, this heavy mineral sand of the Wits. Okay, more to think about.
Yeah.
Yeah.
Nice,
may
Colin.
just add a comment. The evolution of the black sand minerals, magnetite, hematite, and ilmenite, is quite complex in the viz. And it seems very likely that there is early detrital rounded to buckshot pyrite. There's also early pre-gold overgrowth on that pyrite. There's also the breakdown of some minerals like the garnets, as postulated by Neil. But there's also breakdown of other phases. We see quite clearly that rutile tends to survive, but ilmenite becomes a uranium bearing phase, and it changes the whole dynamic of what's going on in the ore zones with time and evolution of the mineralized system in the vicinity of the unconformity. So I mean, there's a great deal that's known or at least postulated as satisfactorily explained by Jonathan and Neil, amongst many other people. And so to talk about black sand is it needs to be talked about, but we're not looking at the rock as it would have looked like when the black sands were initially concentrated as placer minerals, heavy minerals. And therefore, one has to be very careful in saying anything too much about black sands in the viz. Most of the evidence for them is gone.
I think that's thanks for that, Nick. And it's a good caution. It's a lot to be covered if we're going to do pyrites and all those minerals comprehensively, but it's worth doing. I suspect Jonathan Law will touch on some of these next week because in talking about the quartzites, the minor minerals are also very important there too.
And Neil, just a button, you might just get our previous speaker to just send us a note too that we can circulate with those points. You know, he broke up a lot.
Yes.
And, obviously some of you are close to it and some of us are far from it. So it's useful stuff, and perhaps just put a note together and circulate.
Okay.
If you look in the comments column, there's two nice slides by Hilke. He's just scanned the Wits sample of the field.
Can you guys see
it? Pretty amazing looking at it again. I mean, it's would like to get I must get it in sections actually.
So you're doing something useful now that you retired.
Oh yes, I keep on doing that, John.
Good. We'll have to see more of you, and
absolutely.
Would you circulate them as well, and we'll then we can get you to comment on them.
Could you put that up on the screen, Hilke, so we can have a big picture on the record?
Hang on, let me
just share your screen on click on one of those images.
Hang on 1 sec.
You got the share screen button at the bottom, and then you just click on one of your slides. You select it. No, it's just so that if it becomes part of the record, apart from being on the chat side.
See Henny's screen, but
you see, did you click on the green share button at the bottom?
Yeah.
and then you get on your. There we go. If you could just enlarge that, then we've got that on the screen. There we go. Thank you.
Lost it.
Now it's part of the video.
Okay. All right. So we need a note on that as well, Heike.
Can I butt in there? Can we go back to that sample?
The one with the little fractures.
Yeah. Can you? Neil knows what I'm going to do.
There are two of them. One has got fractures, and the other one doesn't seem to be. You want to do that again, Neil?
Just the rock that was up before.
Yeah.
Can I point out that it's just oodling fractures? I don't know if you can see. Can you see me moving my mouse or not?
No.
No.
Oh, okay. Well, there are several fractures. Yeah, that's correct. Also, top, there's one coming down to bottom right. Also, I think that there's a number of positions where you can see sulfide in well, something that could be sulfide. It's a photograph I'm looking at inside grains. And it just doesn't matter. Every time you're shown gold-bearing Witwatersrand, you've got these microfractures.
Where's that from, Hilke? Do you know that?
I'm not sure which reef it is. It was actually given out as one of the GSSA pieces at one stage, probably about 15, 20 years ago. So I'll have to go back.
Nice specimen. Anyway, I mean, there's lots of good stuff there to discuss and keep arguing about.
There's a question from Rob Barnett says, has any study been done on the Zama sluice gold particle size versus overall gold grade? No comment on that.
Well, maybe Graham can comment, because he's probably one of the guys closest to the Zama situation, and they're clearly not down there for nothing. When you look at the Porsches and the fancy motor cars driving around Vearncombe.
Yeah, John, am I audible?
Yes.
Yeah.
Okay. Yeah, I seriously doubt whether a study like that has been carried out. From all accounts, you don't get too close to where these guys are working on recovering gold.
Yes.
I know that from experience. A friend of mine had some years ago where he was shot at.
But they go ahead.
This is Rob Bonnet here. Can I come in?
Yeah, far away.
Yeah, all right. I've seen sort of quite a bit of this. And in fact, I saw a backyard operation just this week with a guy who's using what was his swimming pool to take the fines. And look, I know that there are guys who take the fines and reprocess those further because they're still rich in gold. But I mean, like you say, the guys make money out of this. Well, they survive, put it that way. So we would be, well, anyway, that's one thing I thought might be of interest.
Okay. All right, that's a great session, Neil. Let's wrap it up and
Yep. Okay. Thank you very much. Thanks to Henny and John and the people behind you making the OGG part of this work, and to Dave and Julian. Next week, Jonathan Law. Jonathan's work.
Thanks for the invite, Neil. I shall endeavour to be regular.
All right. Cheers for now, everybody.
Thanks, Neil.
Thanks, Neil. I'll give you a call and we'll have a follow-up discussion. Yep. Great stuff.
Okay.
And thanks to everyone for their contributions.